We said that one can do the spectral analysis of HDB coding also in the same way that we have done for the other cases. However, in this case it turns out that one has to evaluate a considerably large number of the coefficients Rn's to be able to evaluate the power spectral density function, because in all of the previous line coding schemes it so turned out that only a few of these coefficients were non-zero, and they became zero very fast after 1 or 2 or at most 3 coefficients, right? But in this case, because there is a considerable effect of one violation that you do at any point in time to a large time later on as to how data will be represented in time later on, there a considerable amount of correlation exists even for time instants which are largely separated from each other after coding, right? The waveform after coding has correlations existing for large values of n, large values of the index n, and therefore it does not decay to 0 very quickly, which means you have to evaluate a very large number of these coefficients to be able to get some kind of a good idea about the spectrum of HDB codes. Alright. For example, for HDB3 to be able to approximate well, you need at least n equal to 63, right? There are other better methods of doing power spectrum calculation in such situations which we have not considered, but in any case that is outside the scope of our present lectures. But here is a typical plot of the HDB3 spectrum and with respect to the bipolar spectrum. So we find that the mean lobes of both are within 0 to f0, 0 to f0, limited to this band, although the shape of the exact spectrum is slightly better in the HDB3 case because it is limited, it is distributed in a more balanced way in the available spectral band. The last point that we made was that the HDB3 code also has error detection capability just like the AMI code has, which you may see by looking at the basic HDB3 coding that we discussed some time ago. Basically, we introduce a violation, right, after a string of 3 zeros. That is what HDB3 coding does. We can notice that in spite of the fact that we are introducing violations, we still have error detection feature in this coding. For example, let us say an error occurs and this negative voltage appears like a positive voltage here. So what you will see then is 2 consecutive ones with the same polarity without 3 zeros in between them, right, which will be detected as an error, right? And similarly you can see any other kind of error that gets introduced will eventually get detected at the point of another violation, right? So like AMI, HDB3 also possesses error detection capability, and for this reason, because it has a slightly better spectral shape, in fact considerably better spectral shape than AMI, HDB3 is to be preferred over AMI.
So error detection is better than AMI, or is it equivalent?
It is like AMI. Basically, we can do single error detection both with AMI as well as with HDB3. Right? That feature is common to both. So with this, I come to the end of our discussion on line coding. Right? Basically, let us review quickly what does line coding do for us. Line coding helps us to achieve a given power spectral density function. There is one function of line coding. It also helps to introduce certain desirable features in the encoded signal, right? Desirable from the point of view of DC content, from the point of view of timing extraction, from the point of view of transparency with respect to ones and zeros, right? So these are the reasons why we do line coding, and we have considered in detail so far how we can shape the spectrum of a line coded signal by mapping the data sequence to voltage levels in an appropriate manner, right? That is a basic tool we have used so far, that is representing AKs in a particular manner as far as their mapping into voltage levels is concerned. That is, we have tried to control the power spectrum and introduce these desirable properties through control of Sx omega, right? Because let me review. We said that Sy omega is Sx omega into P omega mod square, where P omega refers to the power spectrum of the pulse that is used, basic pulse shape, and this depends on the way we introduce the way we carry out the coding of data into voltage levels, right, as data comes along, right. This is essentially controlled by the coding aspect, whereas this is determined by the pulse shaping aspect. We also discussed one example where the power spectrum was controlled by P omega, namely that of the split phase or Manchester coding, where we deliberately wanted to introduce a null at DC, right, and we said that we could do that by making the area under the pulse shape equal to 0, right. But other than that, largely we have been looking at the coding aspect, and that's why the topic we call line coding, right. It is equally important to look at the pulse shape, right, and now we'll take up this issue, and this is a very, very important issue, as we'll soon see. We'll now look at the issue of how to select this pulse shape that we have been talking about, right, and that brings us to the question of pulse shaping. Of course, pulse shaping will also affect your power spectrum, so that becomes another tool with us to control the power spectrum, and now we'll look at this in more detail, the issue of pulse shaping. What have we done so far? We have looked at PT. We have chosen PT to be essentially a rectangular pulse, right, in all our treatments so far. Which in principle has infinite bandwidth, right. So in principle it has not finite bandwidth but a very large bandwidth, although we have argued that most of its energy will be concentrated in the male lobe of the power spectrum corresponding to the rectangular pulse, and therefore we can say that essentially it is band limited, right, in some sense. That is, if we filter our signal before we transmit, or if the channel is carrying out that filtering for us because the channel is band limited, then most of the energy of the pulse will pass through, but a fraction of its energy will not pass through, right, of the rectangular pulse. That fraction we have seen is small. For example, most of the energy lies between 0 to F0 for most of the line coding schemes that we are likely to use, right. So most of the energy lies in this band, except for polar and some of the allied line coding schemes, in which case it lies between 0 to 2F0, right, and for duo binary it lies between 0 to F0 by 2. So depending on the line coding scheme, the basic band differs, but once we have decided the basic band, depending on the line coding scheme, we know that most of the energy lies in this interval, right, and a small fraction lies outside this band. Okay. Now when you transmit it over a band limited channel, this small fraction which lies outside the band can create problems for us. See, in practice we will not be allowed to use more bandwidth than is allocated to us for a for transmission at a certain rate, right? If you are transmitting at f0 and if you are using a particular line coding scheme and therefore you allocated a certain amount of bandwidth on that basis, you are not allowed to transmit anything outside that bandwidth, which means you have to do band limitation, right? And the moment you do band limitation and this small fraction therefore gets attenuated, it may not cause much distortion, but the little distortion that it may cause can cause considerable problems for us, right? So although the distortion may be small, resulting distortion in what? In the pulse shape, right? You're transmitting a rectangular pulse which has this bandwidth. You're not allowing all its bandwidth to be passed. That means it no longer remains a rectangular pulse. It changes into some other pulse shape, right? That is, it is distorted. This distortion, even though it may be small, it can introduce a very severe problem for us in the form of, this is an abbreviation I am using for inter-symbol interference. Okay, let's talk about this a little more. Yes, please. Of course.
That distortion of pulse too.
I'll just be coming to that. I just introduced the topic to you, but I'm going to talk about it more. What happens when you band limit a pulse? What kind of distortion is likely to occur? This is the main question to understand. Can you say something?
It will be in time domain. It will be infinite time stretch.
It will try to be stretched in time. That is the essential thing. You know from the basic properties of Fourier transforms that something that you limit in frequency domain gets spread in the time domain and vice versa, right? And this is in one of the talks also somebody talked about the uncertainty principle of communication theory, right? And that is, if a function is limited in time, it's likely to have a lot of spreading in frequency domain, and if it is limited in frequency domain, band limited in frequency domain, then it's going to spread out in time domain, right? The rectangular pulse was time limited to its interval, basic interval of 0 to t0 seconds, or 0 to t0 by 2 seconds, depending on whether it was a half width rectangular pulse or a full width rectangular pulse, right? But after band limitation to whatever band you have finally allowed it to use, it will get spread out. That is, it will no longer be limited to this basic time interval of t0 seconds. It will spill into adjacent time intervals, right? Or adjacent symbols, right? Therefore, what you are transmitting, the energy that you are transmitting in a basic interval of 0 to t0 seconds is no longer going to be confined to this interval. It's going to spill over. For example, the rectangular pulse perhaps may become like that, right? Some kind of spreading I am indicated. There can be any number of ways of spreading the pulse. So the energy of this pulse has spilled into this time interval, right? Therefore, now when you do detection of a pulse in a particular time interval, you no longer are sure that what you are looking at, whether it is the energy you are looking at or whether it is some other attribute of the pulse you are looking at, is an attribute of the pulse that was transmitted in that interval. It also has contributions from what you transmitted in adjacent intervals, maybe adjacent and in fact a few adjacent intervals, depending on how much is the spread, how many symbols it spills over into. Alright? So therefore, we get an effect which is called inter-symbol interference. It's a very serious problem in digital communication in band limited channels. Right? Which will denote simply by ISI most of the time. We'll have to talk considerably about this effect as time goes. And this is essentially caused due to pulse spreading. Right? Therefore, let's take a stock of what we have discussed so far. What is our need? Our need is to transmit pulses of the kind AK into PT every t0 seconds. Alright? So AK is the amplitude of the pulse that you want to transmit in this particular time interval. The problem is the channel has finite bandwidth. Okay? Our requirement is that we should be able to determine AKs correctly. AKs need to be detected correctly. Right? And now the next problem is that this requirement is hampered by the fact that this band limitation causes spreading of the pulse. Right? Band limitation causes spreading, and that affects this requirement that AKs need to be detected correctly, because when you are trying to detect AK by looking at the pulse interval corresponding to it, you may also get influenced by what was transmitted elsewhere, right, and may make a wrong decision. The probability of making a wrong decision is likely to increase because of disturbance from other pulses. Right? In fact, you can look upon this contribution from other pulses as also some kind of noise. Depending on whether adjacent pulses are positive and negative, the overall contribution will be dependent on how each of these pulses spills over into the required interval of time into which we are looking. Right? It is some kind of a random noise whose value is unpredictable because it depends on what data sequence is being transmitted, right, around that particular interval, right. So therefore, effectively, one way of looking at the effect of this intersymbol interference is as if your overall noise power has increased. You already have some noise in the channel, right, due to various other sources, and here is another source of noise that has got introduced because of the pulse spread. So the total RMS value of noise gets increased, and once the total RMS value increases, the error probability increases, right. So intersymbol interference indirectly affects your performance. That is, your reliability of determining AKs correctly comes down, reduces. Okay? Is that understood? So, what is the way out? Any suggestion on that? Obviously, one suggestion would be, why not use band limited pulses to start with, because we are going to carry out band limitation, so use band limited pulses, right? But it doesn't appear that we have solved the problem if we use band limited pulses. So one possible solution that you can think of is use band limited pulses. But the moment they are band limited, once again they will be stretched in time, and again it appears that they will cause intersymbol interference. So we have a kind of dilemma here.
So why do you say that even this kind of a band limited pulse will actually stretch out in time?
Any kind of band limitation means that in time they have to be stretched out.
So you're already using band limit, is it not? When we get this thing, we limit it to the band. Already doing that.
So earlier on,
So it becomes slow if you have to split it in time.
No, one question at a time.
so earlier on the problem was that the initial signal has an infinite spectrum,
Right.
and the channel has a limited bandwidth, so the reproduction is not good. But if the original signal itself is band limited, then what's the problem?
Yeah, but that means unless you choose the signal very, very carefully, because it is band limited, that itself is going to be spread in time, and therefore either you have to decrease your data rate depending on its spread, right, or else you have to again live with intersymbol interference. That is the point I'm trying to make, right. It's just the same fact that we have been talking about earlier, that if we suppose we are saying, okay, we'll use pulses whose bandwidth is strictly f0 and doesn't have any more than that, where f0 is the rate at which we are transmitting, then the obvious thing is that it will not be strictly time limited to 1 by f0 seconds or t0 seconds. It will exist even outside t0 seconds. So we have the same problem again, right? Whether the channel limits the bandwidth or whether we limit the bandwidth, the net effect is the same, right? Isn't it? After all, there is a band limitation. So it doesn't matter who limits the bandwidth, unless when I am limiting the bandwidth, I do also something else, which is what we are going to talk about. No, not clear? Why not?
The problem is, you said about the stretching in time.
Yes.
Well, stretching in time is there because when you're trying to reproduce the older signal, we don't get the older signal. But
No, that is not the point. It's not a question of reproducing. It's simply a question of, okay, let me talk about that first. We have a rectangular pulse which the channel, which is being passed through a channel with limited bandwidth, right? That, let us say, has this kind of a frequency response, strictly between 0 to f0, because we are not allowed to transmit outside it, right? It is this fact which spreads this rectangular channel into, it stretches it outside the time interval, right? Now whether I do this band limitation or whether the channel does this band limitation, this fact cannot be altered.
So if the rectangular pulse we anyway feed a signal which is anyway band limited, then the output signal will also be the same signal.
No, how will you do that band limitation? The band limitation that you are going to do of a rectangular pulse, how will you do it? You will also do it in the same way, right? So therefore, it doesn't really, it doesn't matter where you are doing this band limitation. That is the point of, I don't know, I think I have said all that I can say in this matter. It seems to be simple enough. Is there anybody else with this doubt? The point that I am trying to make is that band limitation seems like a solution, but unless we do something special about it, is not really a solution, because any kind of band limitation, any kind of band limited pulse that you can think of is likely to be stretched considerably in time, right? And if you are required to transmit at the same rate as before, we have a difficulty here, right? And that is the dilemma I was going to talk about. That it seems that no matter what we may do, whether we limit the bandwidth or whether the channel limits the bandwidth, there is going to be intersymbol interference, which seems cannot be avoided. So either we have to live with it or we have to do something about it. And the answer to this dilemma was provided long ago by a gentleman whose name you are very well familiar with by now. His name is Nyquist, right? And this result due to him, which enables us to use band limited pulses and still eliminate intersymbol interference, was provided as long ago as 1928, right? In a classic paper that is still referred to greatly. And the answer is, answer lies in using a properly shaped band limited pulse, right? So we'll of course try to understand what that proper shape is. Use a properly shaped band limited pulse. And what is a proper shape? This is what we need to understand, right? Now to do that, he suggests a criterion which is known by the name of Nyquist's criterion. There are a number of them. At the moment we will discuss the first criterion, but I'll just call it the Nyquist's criterion. Okay. This is a criterion for using band limited pulses with zero intersymbol interference. Okay. Now before we take up this criterion, let us see what we understand by this proper shape. Okay. And to do that, I have to slightly digress. Let's look at the basic. I'm not going to go into the details of a digital communication system, but I want to look at functionally basic building blocks of a communication system, digital communication system, from the point of view of pulse shaping, which are relevant to pulse shaping. We're not again going to review what the whole system looks like. We have already seen that. But from the point of view of pulse shaping, you can think of the following basic blocks. You have a pulse coming along. You have data coming along. Let's put it that way. You have data coming along in the form of ones and zeros, which I can represent by, let us say, impulses of appropriate strengths. Right? Let's say the kth impulse has a strength a sub k, and therefore data at time kt is being represented by an impulse with strength ak delta t minus kt. Right? I can assume that this is being passed through a pulse shaping filter at the transmitter. So this is a filter with impulse response, which I am denoting by P sub t, the subscript t here denoting the transmitter. Okay, and obviously what I will get here at the output of this is a superimposition of these pulses. The pulse shape here will depend on the transfer function of this filter or the impulse response of this filter. Right? So if at the input to this filter the signal is a sub k delta t minus kt summation over k, right? That is the input. The output will be a sub k pt. Convolution of this with an impulse will be simply pt, the pulse delayed by kt, right? So this is what you will get at the output, right? This is how you typically can do pulse shaping at a transmitter, by choosing a filter, pulse shaping filter of an appropriate impulse response. Now this is going to go over a channel. I am not going to other functions, other blocks of the system, but broadly speaking, just before you transmit, let's say you have done this pulse shaping, and this is going through a channel which has a transfer function at c omega or an impulse response at ct. Right? Finally, at the receiver, among other things that you do, as far as detection of AKs is concerned, we have agreed, although we have not discussed the theory of that so far, that we will use some kind of a match filter. Right? So anyway, there is another third filter coming into the picture at the receiver, right, which has perhaps an impulse response P sub RT. Okay? Alright? Now let us see what I am trying to say. How will you process the output of this P sub RT? I have got the same picture again drawn over here, so please look at it a bit carefully. Here is your transmitting pulse shape filter, here is your channel, and here is your filter at the receiver, which could be a match filter or any other kind of detection filter which helps us to do reliable detection. Okay? Basically the idea of this filter is to average out the noise in each pulse shape as much as possible and to get at the output some value, some signal which is proportional largely to the signal rather than to the noise. And typically what you will do is the output of such a filter, match filter, will be sampled every kT seconds, and depending on whether the sample value is, let's say, above a threshold or below a threshold, you will declare a 0 or a 1 to be present. Right? This is the broad manner in which things will be done in a digital communication system from the point of view of a pulse that is transmitted, affected by the channel and processed at the receiver. Okay? So from the moment that you have these impulses coming in, with which carry the data for you to the point at which final decisions are taken, you have 3 filters coming to the picture, right, which you can club together into a single filter, which I'll call the pulse shape here, PT. So the pulse shape I'm going to talk about for the time being is not the pulse shape that is going to come out at the transmitter, but which is what you're going to look at just before you do the sampling here, because it is that pulse shape which is really important as far as inter-symbol interference is concerned, because at the point of detection it is important that I don't have interference from other symbols, right? Where is it important that there should be no inter-symbol interference? At the point at which I'm going to decide whether AK was 0 or 1, right? At that point I don't want any interference from AK, what was AK minus 1, how AK minus 1 was transmitted, how AK minus 2 was transmitted, or how AK plus 1 is going to be transmitted, and so on, right? So at the sampling instance of this pulse shape, if I don't have inter-symbol interference, I have done the job, and therefore what I really consider is an equivalent system whose impulse response is simply PT, which is the convolution of this PT, P sub T, the channel impulse response H sub C, and the receiver filter P sub R, right? So PT is an impulse response of the overall system, overall baseband system, and given by PT star convolved with HC convolved with P sub R. And let us work with this equivalent system here. Okay, the input to this equivalent system is the data sequence impulses, impulse train carrying the data sequence, represented like this. Output is a pulse train sequence with pulse shape PT minus KT, right? And will now allow this PT to be a band limited impulse response, strictly band limited impulse response. Okay. Any questions so far? And now let us return. We are ready to return to the Nyquist argument. What Nyquist proposed was that one can achieve 0 inter-symbol interference if we choose this PT such that it undergoes a 0 crossing every t second except for t equal to 0, right? That is, if we choose a PT, pulse shape PT, which is, let us say, equal to some finite value 1 at t equal to 0, but is ensured or guaranteed to be 0 at all other sampling instants, t equal to kt, k plus minus kt, let us say, k not equal to 0. So choose the overall pulse shape PT such that this property is satisfied. Do you appreciate this? This is the important contribution of Nyquist. That is, if we do that, we note that at the sampling instance we will not get any contribution from, because when I'm sampling in the kth time interval at t equal to kt, the only non-zero value from this summation will be coming from the kth pulse. All other pulses will be going through a 0 crossing at that point. So even though this summation is what you are really observing, right, the only term that contributes to the summation at the kth time instant is coming from a sub k, and you will detect a sub k correctly. What a simple ingenious argument, right? And that is the original contribution of Nyquist way back in 1928 to eliminate inter-symbol interference. So you let the pulse to spread out, it does not matter. Make sure that it has regularly spaced 0 crossings every t0 seconds, where t0 is your time interval of every bit, Okay, this is a basic, very simple, ingenious argument given by Nyquist. Choose a pulse shape PT such that it has this property. All of you understand this? Because if this is understood, you can understand the Nyquist theory in very easy way. This is a basic important point. Rest is all maths, which is very easy to follow. So such a pulse shape will achieve zero intersymbol interference at all the remaining sampling instants. Okay, I'm talking of, this is a zeroth pulse. It is going to spill into the remaining pulses that you are transmitting, but at their sampling instance, sorry?
ISI means its interference with the other with the remaining ones.
Right, it will not interfere with the other pulses at the sample at their sampling instance. The pulse that you transmit at time 0 will not affect or will make no contribution to the pulse that is transmitted at t equal to t0. It should be t0 here at the sampling instant t0. Right? There will be intersymbol interference as such. Right? They will keep on spilling into each other and adding into each other. By the sampling instance, there will be no effect.
But synchronization will be very crucial.
That is very important. That is crucial anyway. In digital communication, it is crucial anyway. But yes, this is an important point which one has to worry about, because a small timing error will destroy this zero crossing property. Right? It's a very important point I made, and we'll return to this point soon enough. Right? We'll see that that point also matters to our choice of pulse shape. We'll soon see that.
So do we assume that the pulse is band limited?
That's right. We are, see, that's the point. We are saying that the pulse may be band limited and therefore stretched in time. But we don't care as long as that stretched out pulse has this property. Right? That is important. Okay? Can we proceed further? Now let us look at some questions. Maybe let me ask you this question. Suppose I ask you, how many such pulse shapes exist? What will be the answer? Infinite number of pulses. Because what we are saying, that here is you want to find a band limited curve which passes through this point and which passes through all these points, right? And you can think of infinite number of functions which will do that for you, right? Suppose I ask you, the next question is, suppose I ask you, what is the smallest bandwidth pulse such that, right, very good, smallest bandwidth pulse with bandwidth 1 by t0, right, which will pass through these functions. It is a sync pulse. Very good. The smallest bandwidth function which will pass through these points is the sync function, right? So now its extent is infinite. We are using an infinite pulse duration, but we have ensured that it is band limited strictly to, what is the band limitation, band interval? Not 1 by t0. It is, sorry, the smallest bandwidth required is not 1 by t0, 1 by 2 t0. In fact, that is the correct answer. I'm sorry, I made a mistake. 1 by 2 t0, because the sync function corresponding to that will have a width. We'll call this frequency 1 by 2 t0 as f0 by 2, right? This is minus f0 by 2. Okay? Now I've drawn that better here. You can look at it again. If you have the spectrum shaped like this, p omega shaped like this, then we'll have a regular zero crossing every 1 by f0 seconds or every t0 seconds. So that's the kind of pulse shape we need to use. right? And we already have one answer as to a band limited pulse which will have this property, namely the sync pulse. Not only it will have this property, it has a very small required bandwidth. It is in fact since it is the smallest bandwidth pulse which will have this property, we say that the minimum bandwidth required to transmit data at the rate of f0 is f0 by 2. This is where that minimum comes from, which I have talked about a number of times in the previous lectures, right? The smallest bandwidth required to transmit data at a rate of f0 per second, f0 bits per second or f0 symbols per second is f0 by 2 hertz, right? And the way to do this is to use a sync pulse for transmitting your data. Of course, you must remember that the pulse shape you are referring to here does not refer necessarily to the transmitted pulse shape. In fact, that is not important, what you really transmit. What is important is that the combined effect of the transmitting pulse shaping filter, the channel filter and the receiver filter should look like this. This is what is really important, right? The actual pulse shape that goes onto the channel is not that important, right? Alright. Now, is that all or should there are problems here? Let's just before coming to that, note that this function is sync f0t, right? I am assuming that this amplitude here is 1, and this function here, which is a Fourier transform of this, is 1 by f0 or t0 rectangular function with width, well, in f domain it is f0, in omega domain it is 2 pi f0, right? And these are Fourier transform pairs. And such a pulse shape can be generated by passing an impulse through a filter of this kind, right? All that is very clear. Let us talk about some practical problems with this pulse shape. One problem has already been pointed out by your friend, and that is a small timing error which may be due to maybe the transmission rate is slightly changed, due to instabilities of the clock. Maybe your sampling rate at the receiver is slightly changed due to again instabilities of the clock, or maybe your timing extraction circuit has some timing jitter associated with it. After all, no timing extraction circuit will be perfect, right? Noise will affect the performance of even these timing extraction circuits, right? So if that is the case, the points of sampling will change with respect to the zero crossings, right? Now that is going to create trouble. We'll talk about that. So the practical problems that you must worry about are errors in maybe your transmission rate, or maybe errors in your sampling rate at the receiver. Right? Or there may be a timing jitter, a small timing jitter. That is, your recovered clock at the receiver does not have fixed timing interval from one to the next, but there is a small jitter in it at the sampling instance, in sampling instance. Now in any of these situations we can again come back to the same problem which we wanted to avoid, namely intersymbol interference. Is that clear? Because this summation AKPT minus KT, again at the sampling point, if all the other pulses are not being looked at as being 0, they will contribute to your sample value here, right? And they will again introduce intersymbol interference. So the net effect is that any of these situations ISI will be back. right? Intersymbol interference will reappear because of this problem. Now, particularly the sync pulse is bad for this, from this point of view, for various reasons. One is this function, it decays too slowly for us, right? So if the function decays very fast, a slight timing error will not cause that much of timing, will not cause that much of intersymbol interference if it decays very fast. What is the rate at which it decays asymptotically with respect to time? Asymptotically, it is sin x by x. So asymptotically it decays as 1 by t, right? So that's a bit too slow. In fact, you may know that the main lobe of this is only 13 dBs below, the side lobe, the first side lobe of this is only 13 dBs below the main lobe value. If you take the ratio of this to this, peak values, it's only 13 dBs in magnitude, which is not much. That means a small timing error can have a potential large ISI associated with it. Number one. Number two, the slope at the zero crossing is quite large, right? So, and what will that mean? That means even small timing errors will cause considerable shift from the zero value, and therefore considerable amount of intersymbol interference. All right. So let us notice these things. Sync pulse disadvantages. One is that decays too slowly, right? Only as 1 by t asymptotically. Side lobes are too large, particularly the first side lobe is very large, right? And third is has a large slope at zero crossings. Right? All of which are bad things for us as far as robustness to timing errors is concerned. So this is a basic pulse shape which satisfies your Nyquist requirement that it wanted, but it is not robust to timing errors. Right? This pulse shape is not robust to timing errors.
Can you explain how does a large slope matter?
Right? Very easy. If you have a large slope at the zero crossing, what it means is if instead of sampling here, end up sampling here, right? Because there is a large slope, the difference from zero will be large, right? If you instead of sampling here, you end up sampling here, right? Because there is a large slope at that point, that means the build up is large. Build up of a non-zero value is very fast, okay? So we would prefer to have as small a slope at zero crossings as possible, right? Okay. What is the reason for all these things in a sync pulse? Why does sync pulse has its bad properties? The reason is, if you look at the corresponding Fourier transform or the spectrum, it has a sudden, in fact a very sharp abrupt change from a non-zero value to a zero value. Any function which is very, very sharp in one domain will exhibit such oscillatory behavior and such bad properties in the other domain, right? So the answer therefore lies in making that fall gradual rather than too sudden.
Trade-off between bandwidth.
That's right. Very good.
So you said the decay is too slow.
That's right. Decay of the pulse shape or pulse values.
Won't be required to be slow so that even the steadily t plus delta, 0 plus delta t must remain the same value.
I didn't get your question.
As you said, for the zero crossing,
Yes.
if the slope is less, so even if there is time shift, we retain that value. Same for the impulse at t is equal to 0.
Yes.
If there is some shift, we retain the same value of slope is less, isn't it?
But that will be an error. That is an error.
So what is your question?
That is
If
an
there
error.
is slope is too slow, it has to, if the flow wave is
No, I thought you were talking of decay. What are you talking about?
decay,
Decay, asymptotic decay. See, if asymptotic decay is fast, that means its ability to interfere with pulses which are far removed from it will become small, very fast. If on the other hand, if its asymptotic rate of decay is slow, right, it will have considerable amount of side lobes, even with pulses at the location of pulses which may be a few symbols away from it, right? So its potential to cause intersymbol interference over large intervals increases if the decay rate is slow. That is the significance of slow decay. Alright? So therefore we like to have a large decay rate so that its potential, if at all it has a potential to cause intersymbol interference, it is limited to only a few symbols around it and not to many symbols removed far away from it. Okay? That is the significance of that point. Now anyway, returning back to the disadvantages of the pulse shape, we note that all these disadvantages are essentially contributed by the fact that it has a sharp discontinuity in the frequency domain, in P omega or PF, right? So if we can get rid of this sharp discontinuity and also ensure that whatever we do in such a manner that zero crossings are maintained, then we are perhaps in business, right? We may of course have to increase the bandwidth, isn't it? Because this was the smallest bandwidth pulse which could satisfy that requirement. So therefore, any other shape which has a gradual cutoff rather than a sharp cutoff is necessarily going to have larger bandwidth, but may introduce a better reliability in terms of timing errors, right? Robustness to timing errors. So the question therefore that we need to look at is, can we find a pulse shape PT that satisfies the Nyquist criterion, that satisfies that equation which says PT should be equal to 1. Let me call that equation as equation number 1, this particular equation. Right? We are calling this equation as equation number 1. Okay? It satisfies this equation and decays faster, right, and has all the other nice properties that we want. The answer is yes, but at the cost of some bandwidth, right? Requires bandwidth which is greater than the minimum f0 by 2, right? Typically what we'll work with is a bandwidth value kf0 by 2 where k lies between, let me say kf0 and k lies between half and 1. Let us prove that we can do such a thing. Can we direct the discussion this way? It will be better. Yes, speak out your question.
He was talking for exponential pulse.
Exponential pulse.
If we could,
Let's have your suggestion, whatever it is.
we could multiply this thing by something, we could make it decay exponentially.
That's right. Well, exponential decay will be a bit too much, but at least polynomial decay should be possible, right? And that's what we will see is possible. That is 1 by t to the power n rather than 1 by t, right? Which is what you want? We will try to do that. Okay, just wait. So let's look at the proof of the statement that we have. Okay, I think we should take that up next time. We're just finishing in time. So we'll see a non-sync pulse, that is one which is not a sync function, satisfying this requirement and having slightly larger bandwidth than this. Thank you very much.